We'll now put our equation for delta G and our spontaneity condition involving delta G into action when we take a look at some example problems that will show the temperature dependence of spontaneity and help us to predict if a process is spontaneous or not at a given temperature. What we're going to do here is consider the vaporization of benzene, or that's C6H6. So vaporizing benzene has a delta H of vaporization at standard conditions of 30.77 kilojoules per mole and a standard delta S of vaporization of 87.1 joules per mole per Kelvin. We have to predict whether or not C6H6 will boil at 60 degrees Celsius in 1 atmosphere, and if it doesn't, we need to figure out at what temperature it will spontaneously boil. So let's talk about how we can use the delta G equation to help us find this. We know from our previous video that delta G is equal to delta H minus T delta S. And I'm putting these superscript zeros here because we are at standard conditions in this problem, right? We're dealing with a 1 atmosphere pressure. Now, importantly, in this equation, you must use Kelvin. So with that in mind, let's go ahead and calculate the delta G for this process at standard conditions. We were told that the delta H standard was 30.77 kilojoules per mole. So we'll plug that in, minus the temperature was 60 degrees Celsius, which is 333 Kelvin. And the delta S, we were told, was 87.1 joules per mole per Kelvin. It's important to always be writing out the units because when you do, you recognize that you have an incompatibility in the unit. One term is in kilojoules per mole, and the other term is in joules per mole. You have to make the units compatible, and what I'm going to do is convert the joules from delta S into kilojoules. So 1 kilojoule is 1,000 joules, and now we're going to have compatible units. The kelvins cancel, and the joules cancel, so I'm left with kilojoules per mole for both terms. What we find is that the delta G, under these standard conditions, comes out to positive 1.77 kilojoules per mole. Having calculated the value of delta G, we can now predict if this process is spontaneous or not at 60 degrees Celsius, or 333 Kelvin. And because delta G is greater than 0, this process is not spontaneous at this temperature. Remember that the spontaneity condition requires delta G to be negative for a spontaneous process, right? So benzene will not boil at 60 degrees Celsius, but rather, if you had benzene in the gas phase, it would spontaneously condense at that temperature. So having found that the process is not spontaneous at 60 degrees Celsius in 1 atm, the second part of the problem asked us to determine at what temperature it will spontaneously boil. So let's go to the next slide and do that part of the problem. Now, before we do the calculation, it could be helpful for us to make a prediction. So if benzene doesn't boil at 333 Kelvin, what do you think you'd have to do to the temperature to make it boil? Do you think you'd have to raise it or lower it? If we're talking about boiling, you probably would want to raise the temperature in order to make the liquid boil. And so we're going to expect that the temperatures are going to be somewhere above 333 Kelvin. Let's do the calculation, and hopefully that will be what we get. So to find this, what we should do is start by writing the spontaneity condition, because that is going to be what determines whether or not the process will happen. So we're going to start with the spontaneity condition, which is to say that delta G has to be negative. Now, we can relate that to given information, right? We can relate that to the information that we were given about delta H and delta S by looking at the equation delta G equals delta H minus T delta S. So what we're going to do is now make a substitution to combine the two equations. So delta G standard is less than 0. Delta G standard could be rewritten as delta H standard minus T delta S standard. So you can say delta H standard minus T delta S standard has to be less than 0. That's the same thing as saying delta G is less than 0. All right. Now that you've combined the two equations, you've now re-expressed the spontaneity condition in terms of variables that we do know, right? Because we know what delta H and delta S are. At this point, it's going to be a matter of solving this inequality for temperature. to find what temperature the process is spontaneous. So what I'm going to do is first add T delta S to both sides to get me delta H is less than T delta S. Now, normally I would solve for the variable of interest before plugging in the numbers. But in this case, I'm going to plug in the numbers at this point in time before I've solved completely for temperature. And you'll see why in a moment. So we'll plug in the delta H value of 30.77 kilojoules per mole less than T times delta S standard, which we were told was 87.1 joules per mole per Kelvin. All right, now at this point, to solve for T, you would divide both sides by the value of delta S, which is 87.1. The reason why I've chosen to plug in the variables now before dividing is because in this problem we're dealing with an inequality. And so things can get a little bit tricky depending on the sign of a value that you're multiplying or dividing through the inequality with, right? In this case, the value of delta S is positive. So when you divide both sides by the value of delta S, that's not going to change how we would represent this inequality. But if delta S were negative, right, if it were negative 87.1, what happens to an inequality when you multiply or divide by a negative, right? That causes the inequality to flip. So you have to be aware of that. You have to be careful for that. And you have to recognize when you're dealing with a situation that would require you to flip the inequality. If delta S were negative, you would need to do that in this case. And having the value written in there would indicate that to you. Now, because this problem has a positive value of delta S, we do not need to flip the inequality. All we're doing is simply just dividing by 87.1. So we get 30.77 kilojoules per mole over 87.1 joules per mole per Kelvin is less than T. And you have to make the units compatible. So we've got to either convert kilojoules to joules or joules to kilojoules. Doesn't matter what you do, the units are going to cancel out either way. I'm just going to convert the joules into kilojoules. So 1 kilojoule is 1,000 joules. And in terms of the units here, we have joules cancel, and now kilojoules on the bottom, kilojoules on the top, that cancels. Moles and moles cancel out, and I'm left with just Kelvin. And that's a good thing because I'm finding a temperature here. The number that I get is 353 Kelvin is less than T. Or you could also rewrite that as T is greater than 353 Kelvin, meaning that at a temperature above 353 Kelvin, you should be able to boil the benzene. So this delta G equation is really powerful because it allows us to not only predict that a process is not spontaneous at 333 Kelvin, but it also helps us to predict what temperature you would have to raise the system to in order to make the process spontaneous. If you were to heat it up to 353 Kelvin, then you would be able to boil the benzene. And this is consistent with the prediction that we made at the outset here, right? We said that for boiling, 333 Kelvin wasn't a temperature that would work for us. If we wanted to boil it, we would probably have to raise the temperature. And sure enough, we find you have to raise the temperature to make that happen. Now, it is possible to have a situation where a process will be spontaneous at all temperatures. So I want you to think about what combination of signs for delta H and delta S would give you a reaction that is going to be spontaneous at all temperatures. Take a moment to think about this and put in your answer. Having given you some time to think it over and work out the answer, let's talk through it together so that everyone knows how you could arrive at the right result here. The way that I like to do this is to start by writing our equation delta G equals delta H minus T delta S, because that equation is going to help us to relate delta G to delta H and delta S. And what we see here is that this equation, right, delta G is composed of two terms. We have a delta H term, and we have a negative T delta S term. We're going to consider both of these terms independently of one another. Now, what we want is for the process to always be spontaneous. And so what we want is delta G to be always negative. In order for delta G to always be negative, both of these terms have to be negative. Delta H has to be negative, and the negative T delta S term has to be negative. Because if both terms are negative, then both terms will favor spontaneity, and the process will always be spontaneous at any temperature. Now, how are we going to achieve that? To have a negative delta H term, you would have to have a negative sign for delta H, meaning that the process would have to be exothermic. If the process is exothermic, then that favors spontaneity. The reason why we say it favors spontaneity is because that has a negative sign associated with that term. And again, we want delta G to be negative to be spontaneous. Now, let's think about how we make the negative T delta S term negative. So in this term, we have a negative sign out in front. Temperature is always positive because we use the Kelvin scale. And remember that on the Kelvin scale, the lowest possible temperature is 0. You can't have negative temperatures in Kelvin. So temperature is always going to be a positive number here. And so in order for this term to be negative, the value of delta S has to be positive, because if you have a negative times 2 positives, that gives you a negative value. Then you're going to have a term that favors spontaneity. So when you have delta S greater than 0, that will also allow you to have a situation that favors spontaneity. Therefore, if both terms favor spontaneity, then the process will always be spontaneous, regardless of the temperature that you choose. So when delta H is negative and delta S is positive, your process will always be spontaneous. There are examples of some combustion reactions that would fit this description. If you have a combustion reaction, that's going to be an exothermic reaction, and so delta H will be negative. And if in the combustion reaction you were to increase the number of moles of gas that you have, if there were more moles of gas in the products than in the reactants, then you would have a positive change in the entropy of the system, because gases are higher in entropy, they're more random than liquids or solids. And so you would have delta H negative, delta S positive. That would be spontaneous at all temperatures. Let's take a look at some other combinations of signs for delta H and delta S and what that means for spontaneity. Now, what about a situation where delta H is positive and delta S is positive? So for that, we can again look at our delta G equals delta H minus T delta S equation and break it down into the two terms that we have here, right? A delta H term and the negative T delta S term. We've been given that delta H is positive, and so that's going to make the delta H term positive. This opposes spontaneity because positive numbers are not good for delta G if we're talking about spontaneity, right? We want delta G to be negative. As for the negative T delta S term, delta S we're told is positive. Temperature, again, is always positive because we use the Kelvin system. The negative out in front gives you a negative times 2 positives. That makes this term negative, and so this term favors spontaneity. And so now we have a situation where one term favors spontaneity and the other opposes spontaneity, right? So there's going to be like a battle between these two terms to determine whether the process is spontaneous or not. If you want the process to be spontaneous, then you have to make this negative T delta S term, the one that favors spontaneity, really big. Because if you have a big term that favors spontaneity, then the process will be spontaneous. That will overtake the term that opposes spontaneity. To make the negative T delta S term really big, you have to pick a big value for temperature. So choose high temperature or a large temperature. And that will make the process spontaneous. So that will allow you to drive the reaction. Even though the delta H term opposes spontaneity, if you make negative T delta S so big and so negative, delta G will end up negative and the process will happen. So what we would say is that this process is spontaneous at high temperatures only. We actually previously saw an example of this when we considered the vaporization of benzene. For that example, we were given the delta H and delta S and both of them were positive, and we found that process was only spontaneous at high temperatures. In this case, it was above 353 Kelvin. Now, how high is the temperature? That depends on the relative values of delta H and delta S, right? So in the benzene example, you needed to go above 353 Kelvin. But in other cases, with other values of delta H and delta S, how high the temperature has to go, right, will vary. Let's consider some other cases. So we're going to wipe this and think about some other cases. We'll think now about what happens if delta H is positive and delta S is negative. We could also think about what happens if delta H and delta S are both negative. And I'm going to have you work through those on your own so that you can get familiar with doing the same type of analysis that you've just seen in the last couple of examples to figure out what the spontaneity conditions are in those cases. And what you'll end up finding is, again, for delta H negative and delta S positive, that's spontaneous at all temperatures. And if delta H and delta S are both positive, that's spontaneous at all temperatures. For delta H positive and delta S negative, both terms are going to disfavor or oppose spontaneity, and so this process will never be spontaneous at any temperature. And if you have delta H negative and delta S negative, you'll have a process that's only spontaneous at low temperatures. Definitely practice with that on your own so that you can get to the same result by going through that analysis that I have described over the past couple of examples.